Okay, so now I have ways to get limits. From the law of large numbers, I get a limit. I get 2 almost sure in probability. And from the central limit theorem, I get another limit. We're going to want to combine those results. Maybe we're going to have one estimator for the mean, for which we're going to have a result that looks like this. But maybe we won't know what sigma is, so we're going to have another estimator for sigma. So we're going to replace this by sigma hat. And then we're going to just have something that looks like maybe we're going to have sigma hat, sigma over sigma hat, something like this. And this guy, by the law of large number, is going to converge to 1. The other guy is going to converge to a Gaussian. How do we combine those things? Right? How do I combine several limits, multiplying them, adding them? So when you're actually almost sure and in probability, things go exactly the way you want. You can add your random variables. You're going to come to the sum of the limits. You can multiply them. You're going to come to the product. And you can divide them, and you're going to come to the ratio, as long as your ratio is well defined, of course. OK? So this is the slide that says, do not pay attention to mathematics. It works the way you want it to work. Now, of course, there's at the bottom of the slide, there's this thing that says that convergence and distribution, the problem is this thing is kind of weak. And we cannot say things like this for very obvious reasons. If I tell you that Tn converges in distribution to T and Un converges in distribution to U, those things don't have to be, doesn't mean anything to add them, right? Like, what is the correlation between T and U? Or like, this makes no sense. And so they don't live on the same probability space. All I'm telling you is that the probability of the distribution of this guy converges to the distribution of this guy. So those things are actually not going to happen actually almost all the time. But still, I want to be able to do this. So I have a convergence in distribution. So I would like to multiply it by another convergence. But hopefully, this convergence is strong enough. This is convergence in probability to a number 1. And that's going to help quite a bit. So let's see what happens for convergence in distribution. So there's something called Slutsky's theorem. And Slutsky's theorem tells us that if you have 2 sequences of random variables, and the first one converges in distribution to some other random variable t. So the distribution of this guy converges to the distribution of that guy. Think this thing. Square root of n xn bar minus mu divided by sigma. This thing converges to a standard Gaussian. Then you have u, which converges in probability to a single number. It's just a scalar. Now it starts to make sense for me to talk about the distribution of t times u, for example, because if this is a Gaussian, then this is u times the distribution of a Gaussian, which is an n0 u squared. So this thing actually makes sense. Now here, u would be the limit of sigma over sigma hat, which we claim will be 1 by law of large numbers. Eh? And so in this case, I can actually do this. And when I can do this, that's what Slutsky tells me. He says that now you can add limits. You can multiply limits. And you can actually look at ratios when those things exist. So this will actually be t over u. OK? And so that's basically what Slutsky is telling us. So it tells you can do it only if and only if essentially one of the limits is actually just a deterministic number. OK? And if you think about it for 1 second, this would not make any sense if u was not a deterministic number. This neither. OK. Here's an important one, which is the continuous mapping theorem. So it says that if you have Tn that converges to T, then f of Tn converges to f of T in all 3 senses. So almost sure, in probability, and in distribution, respectively. And this is called the continuous mapping theorem. So it's very important that the function is continuous. OK, so for example, how do you use this? Well, I know that Rn converges to P, then f over n converges to f of P, if f is continuous. That also works for convergence in distribution, see? So I know by the central limit theorem that this quantity converges to a standard Gaussian. So f of this quantity converges to f of my Gaussian. So I should write f of square root of n Rn bar minus P divided by square root p1 minus p. And that should converge to the, sorry, I'm sorry, I made a mistake. So this is actually, I just wanted to make it a little bit of an exercise. This is y, so it's not z. So I need to multiply everybody by square root of p1 minus p. So this thing is really just this guy without, this thing is really this guy. There you go. Okay, let's make it look nice. Okay? So first I multiplied both sides by the square root of p1 minus p so that my variance became p1 minus p. And then I said, well, f of this quantity goes to f of y. Okay? Everybody's fine with this? Now, what we're going to need is not this. This is actually kind of a useless result. We'll never use it again. We'll use that one, but this one not so much. Because what we would really want is to say that how close is f of Rn to f of p? Let's say I don't want to estimate p itself, but I want to estimate 1 over p, or I want to estimate p squared. Then I would need to, a good candidate would be the same function of Rn bar, 1 over Rn bar, or maybe Rn bar squared. This would be a good candidate. But this result does not tell me anything about this. So for that, we actually need to look at something called the delta method, or sometimes delta method. Okay, and we'll see that in the next chapter. The delta method is what you need to use when you want to look at something which is f of something minus f of something, but not f of the whole thing. Okay? So I'm running out of time. There's a bit of a recap on what we've been seeing. I encourage you to take a look. We saw that averages show up, and therefore central limit theorem and law of large numbers. Then we can use standardization, and we can make operations. But for limits and distributions, we need to use Slutsky and be careful.